The figure on your screen shows a discrete common source MOSFET amplifier utilizing the drain-to-gate feedback biasing arrangement. The input signal Vi is coupled to the gate via a large capacitor, and the output signal at the drain is coupled to the load resistance RL via another large capacitor. The transistor characteristics are on your screen. You have to assume the coupling capacitors to be sufficiently large so as to act as short circuits at the signal frequencies of interest. Now your task is to determine the small signal voltage gain, the input resistance, and the largest allowable input signal. So we start our analysis. First we remember to remove all the small signal quantities, and we calculate the DC operating point first. In the drain current equation, we have neglected channel length modulation for the sake of simplicity. The early voltage given to us, 50 volts, is actually for the purpose of calculating R0. We substitute VGS by VD by noting that the current through the gate is 0 because of the large 10 megohm resistance. So essentially, drain and gate are at the same potential, and since the source is shorted, we can simply replace VGS by VD. Moving on, we can write VD as 15 minus 10 ID. Solving this equation together with the drain current equation gives us the value of drain current as ID equals 1.06 milliampere and VD equals 4.4 volts. GM is given as 0.725 milliamperes per volt. The output resistance is also easy to find. It is 47 kilo ohms. Now using these quantities, we draw the small signal equivalent circuit of the amplifier where we replace the MOSFET with the small signal model. But first, if you recall, we have to short circuit the DC supply, and the coupling capacitors are also to be replaced with short circuits. This is the equivalent circuit model. The small signal model with the voltage controlled current source is also known as the hybrid pi model. Now since RG is very large, the current through it can be neglected compared to that of the control source GMVGS. And so the output voltage can be written as, we know that Vi equals VGS, and so the voltage gain can be written as this expression with the value minus 3.3 volts per volt. Next part, we are to find the input resistance Rin. You might be tempted to think that the input resistance is Rg. It is not. Why? Because Rg does not appear in parallel between gate and source. In fact, it is connected between gate and drain. So Rg won't be the correct answer. To find the correct answer, we have to evaluate an expression. This one. We had ignored this current in part A because it was insignificant to GMVGS. However, here it has significance. So solving this, we have this expression and we put in the values to find II equals 4.3 Vi divided by Rg. See, it is not so straightforward that you can say that the input resistance is Rg. It is given by the expression Vi over II, and we can rearrange this term here to find Rin to be 2.33 mega ohms. Understood? Now moving on to the last part. The largest allowable input signal Vi is determined by the need to keep the MOSFET in saturation at all times. Now we have seen that twice, so let's write the condition again. Now remember that Vi equals VGS in the small signal domain. But here we are dealing with instantaneous quantities. So the largest allowable input signal would result in the smallest output signal. Agreed? So we move on from the inequality to the equality. We get this expression. We plug in the values to get this expression. Now notice we have used the modulus around the voltage gain. The value was minus 3.3, but here we have taken the positive value. Why? Because we are only interested in the magnitude. So solving this gives us Vi equals 0.34 volts. Where did this quantity 4.4 and this one again 4.4 come into this expression? Remember, this was the drain voltage at the DC operating point. And the drain and gate are not shorted but connected by a very large resistance through which the current is negligible. So we can assume that VDS and VGS at DC, notice this and this, these are DC quantities, will be equal. So this is how you perform small signal analysis. Note the steps. We are going to be using these extensively throughout the rest of the course, and the more you practice it, the more quickly you are going to solve more complex problems. Good luck.